And using these three, we will try to elucidate a particular molecular structure. Okay. So that is what we are planning to do. As an introduction, basically, by the way, the references will be written on the side, like whatever it is written on this slide, and because of space and other reasons I put it this way, but the reference list is there at the end and I'll send it to you anyway. Okay. uh, just by way of introduction, this is what the electromagnetic spectrum looks like from the context of what is the type of change which is happening in that particular molecule. Okay. So here the example of a diatomic molecule is taken. So we can start with the nucleus and the nucleus spin. And when you apply an external magnetic field, what happens to the nuclear spin? You know that the spin states will split up into a multiple structure like you normally have in Zeeman effect, and then you can get a transition from one spin state to another spin state. This process is called nuclear magnetic resonance, or NMR. And the energy scales, wavelength scales, etc. are given here, which I will not, each time I will not read it out, but you can have a look at that also. Okay. And then you have electron spin resonance, which is the same thing, except that instead of the nuclear spin, it is the electron spin which is active. And sorry, क्या हो गया इसको? Yes. It's the electron spin which is active, and the reason that has higher energy is because the magnetic moment of the electron is higher. If you go back to your basic TYBSc spin angular momentum versus magnetic moment, that comparison, you will find that mass of the particle comes in the denominator. This E by 2m into spin is equal to the magnetic moment. And so if the mass is more, the magnetic moment will be lower, and hence the energy will be lower when it interacts with the magnetic field. So heavier mass, nucleus, the spin interaction is lower energy. Electron spin resonance is slightly higher. Then you have molecular rotations in the microwave region. Then you have got molecular vibrations, which usually fall in the infrared region. I don't know why this keeps happening. And there is someone else wanting to join. Okay, good. I think we are in good numbers today. Huh? Good. Molecular vibrations which happen in the infrared region. Normal ultraviolet or visible spectra which happen due to transitions in molecular orbitals. He has depicted the molecular orbitals like this, which are shared between the two atoms, and atomic orbitals which are centered around one particular atom. And so you have got the transitions among the molecular orbitals, which give emissions typically in the visible or ultraviolet region. And then you have got inner shell processes. The inner orbitals are affected, and that gives you emissions in X-ray. And then finally, the nucleus itself, if it deforms or it changes in some way, then you get emission of gamma rays. So this is the entire electromagnetic spectrum in the context of a diatomic molecule. मतलब diatomic molecule कौन से region में कब emit करता है. So this is the diagram, and I will be passing on this PPT also. Apart from the video, I will be passing on the PPT also, so you can go through it at your leisure. And the reference for this is Banwell. So in the first chapter of Banwell, he has this diagram. You can go through it in detail. Okay. Why I showed this is because we will be concentrating on only two of these, namely NMR, nuclear magnetic resonance, and infrared vibrational spectroscopy. And these two will be sufficient to be able to determine the structure of even very complex molecules. The reasons for this we will come to partially, and part of it will be given to you as homework. But basically, it's very interesting that just two techniques are enough to probe many properties. Some other properties you cannot probe, like ionization potential, etc. Some other spectroscopies are needed. Again, molecular identifications of some specific modes requires you to do ESR or microwave spectroscopy. But we'll come to those one by one if we get time. Okay. Right now, our focus is on nuclear magnetic resonance and infrared. So basically, what is going to be the process by which we work this particular experiment is the following. We will be looking at infrared spectra. As already mentioned, it gives you information about the molecular vibrations, and this in turn can be linked to the different functional groups, that is whether there is an alcohol group is present or a ketone or acid, carboxylic acid or benzene group is present. All these kind of information can be inferred just by looking at the infrared spectra. That is going to be one of the focus points for us as far as this particular experiment is concerned. But it will not tell you some other information. For example, it will not tell you the size of the molecule. It will not tell you what all the molecule consists of. It will give you parts. So if you want to make a map of a molecule, for example, then the infrared spectrum basically gives you features. Like suppose you want to make map of India. One of the thing is you go and from a satellite you take the full picture of India and then you get a map. But infrared spectrum is more like you will see Qutub Minar, you will see Taj Mahal, you will see Gol Gumbaz, you will see Ashoka Stham, you will see various gateway of India. So it gives you specific features, and by looking at those specific features, you have to zero in. हाँ ये type का molecule होएगा. Means is it a map of India? Is it a map of Maharashtra? You can find out by looking at specific features. That is the analogy as far as infrared spectroscopy is concerned. The second technique which we mentioned, nuclear magnetic resonance, this will give you information about different types of nuclei and what is their surrounding within that particular molecule. Example, suppose I give you a simple example. Suppose I give you ethyl alcohol. Ethyl alcohol has hydrogen, carbon and oxygen. But hydrogen has two different situations. Some of the hydrogens are attached to carbon atoms. One hydrogen is attached to an oxygen atom because alcohol means it has a OH group present. So the hydrogen which is in the presence of oxygen will behave slightly differently as far as NMR is concerned than the hydrogen which is in the presence of carbon. Why this is so, we'll look at it later, but you can get pinpointed information about अगर hydrogen present है तो उसके आजू बाजू में कौन कौन हो सकता है. So this is more like you are getting the physical features of that particular molecule. हाँ इसका terrain ऐसा है. So that is like seeing a different feature of the map, not particular landmarks but general land formations. For example, if you have a map of Maharashtra, you will see Western Ghat somewhere, you will see coastal region somewhere. So NMR gives you that type of information. So neither in infrared spectroscopy alone nor NMR alone is capable of giving you complete information about the molecule. Many times you need to do both in correlation. Okay? And the third spectroscopy which we look at is very briefly is mass spectroscopy, which gives you an idea of what is the molecular formula, what is the molecule size, what are the types of fragments which are there. And with the combination of these three types of spectroscopy, we will zero in on one particular molecular structure. And I will be giving you examples as we go along so that we will qualify this particular idea. My idea for this lecture is to give you a very brief theory introduction to all these three types of spectroscopy and how exactly it is going to be useful for the what we are going to do in the practical. Today I will very briefly only touch on what we'll do in the practical, but every week whichever group is having that particular experiment, we can meet and we can go through it in little more detail. So every week like morning, whatever is convenient for you, 10:30 or 11, we can have a meeting, start off the practical, and then evening we'll have another meeting to discuss the different things, conclusions which are arriving at. This is how I am planning for this particular experiment, so called. Okay. So I have broken this talk into a few segments. The first segment is on infrared spectra. how does it originate, what are the types of instruments which are used, and how do you do the analysis. This is basically what we are going to talk about. So as we already discussed, the infrared region is dominated by vibrational modes of the molecule. Okay. And here there is a picture which shows various types of vibrational mode. For example, consider this. This is a triatomic molecule, or this is a CH2 group, which is bonded to something else along the way. There is some other functional group attached at this end and another functional group attached at it. But this is carbon and 2 hydrogen. So what are the different ways in which this can vibrate? Can you see my video? Means can you see me in your screen? Or if you unpin this, can you able to see this? I am waving right now.
Yes.
दिख रहा ना?
Yes, sir, दिख रहा है.
Okay. तो अगर किसी को नहीं दिख रहा तो try to unpin that whatever PPT, then you will be able to see me, because I am going to now vibrate like a molecule. Okay. So what are the different ways in which these are 2 hydrogen and I am the carbon? Okay. So what are the ways in which we can vibrate? One is called the symmetric stretching mode. See, this is one way of vibrating, na? So the center atom stays where it is, other 2 are symmetrically moving. The other is asymmetric mode. But these are all stretching vibrations because the movement is only along the bond direction. Okay? There is a carbon to hydrogen bond and there is movement only along that direction. Both the hydrogens can move like this, or you can have this. These are the first 2 modes which are shown, which are called as stretching mode symmetric and stretching mode asymmetric in the diagram. Then you can also have, see, my bottom part is stationary, only my top part does this. That is called rocking vibration naturally, because it is like a rocking, like that. Okay. Then there is something called scissoring vibration. What is scissoring vibration? So rocking and scissoring are different from symmetric and asymmetric stretch. Why? Because symmetric asymmetric stretch occurs along the direction of the bond, and scissoring or rocking happens perpendicular to the direction of the bond. Bond is like this and this is happening perpendicular to that. Okay. So you have got this along the direction of the bond type of thing. You have got perpendicular to the bond direction kind of thing. Okay. And you also have the rest of my body is stationary and I can have rocking out of plane, which is called as wagging vibration. This is rocking. My remaining part of my body remains stationary, remember. So if it is in the plane of the molecule, it is called rocking. If it is out of the plane of the molecule, it is called wagging. If it is out of plane and antisymmetric, it is called twisting, because I am twisting na, along my waist. Okay. So every molecule, even something as simple as 4 or 5 atoms large, can exhibit all these different types of vibrational modes of excitation. So if basically a molecule ऐसा मरा हुआ पड़ा है, उसको मैं energy देता हूँ, it can do various things. कम energy मिला, हाँ, ज़्यादा energy मिला, और ज़्यादा energy मिला. So different vibrational modes which are shown in this diagram will have different amount of energy associated with it. Okay. And you can already imagine that if I want to predict all of these using proper quantum mechanics, etc., it is a very, very cumbersome, difficult, and nearly impossible task. Quantum mechanics finds it difficult to treat things like lithium atom or something. Molecules are one step more difficult, and molecular vibrations are extremely difficult. It can be done with TDDFT kind of calculations, but there is no need. And why there is no need is what we will come to soon. Functionally, it does not hamper you in any way. Okay? Because you are able to use these particular informations in a useful manner. These are just an example of different types of vibrations which are possible in a molecule, and these vibrations will give a signature in the spectrum. So basically, this is how a standard infrared spectroscopy works. Infrared spectroscopy is normally done with a technique called Fourier transform infrared spectroscopy. This is by far the most common, so I felt it is worth discussing. It's very important. So basic thing, normally any spectroscopy works this way. You have source, then you have sample, and then you have detector. Source will emit radiation, sample will absorb part of the radiation, detector will detect the remaining radiation. So the detector will basically tell you the transmittance of the sample, whether it is transmitting or not, that kind of thing. In Fourier transform spectroscopy, there is an additional component here, which is called an interferometer. All of you have already studied Michelson interferometer. At least I hope you have studied, because that was my experiment last year. But I hope all of you are familiar with that. If not, it's a good idea to revise it before you actually start thinking about this particular spectroscopy. But basically, in a normal spectroscopy, you have source, sample, and detector. सोर्स में से रेडिएशन निकलता है, सैंपल पार्ट ऑफ इट अब्सॉर्ब करता है, बचा कुचा रेडिएशन डिटेक्टर पे जाता है. यू नो हाउ मच रेडिएशन वाज ट्रांसमिटेड बाय द सैंपल. दिस इज द स्टैंडर्ड वे स्पेक्ट्रोस्कोपी वर्क्स. Here what you are doing is you are adding another component in the middle called an interferometer. What the interferometer does is very interesting. In fact, it is written over here that the spectrum which you record is actually not a spectrum. It is something called an absorption pattern in wavelength domain. As a function of wavelength, you can find out which wavelength is means you will get a complicated pattern as a function of let us say time or something, and then you take Fourier transform of that, and Fourier transform of a wavelength signal will become a frequency signal, and you will get a spectrum as a function of frequency. Let me show you an example which will not clear up things completely, but at least give you an idea what I mean. I hope you can see that this sample which is there on the left, the signal, it is having some kind of oscillatory behavior, and then it has a large oscillation somewhere here, and then again it has an oscillatory behavior. This particular signal is called an interferogram. It is basically the signal coming out from a Michelson interferometer kind of experiment. If you remember last year's experiment, because you have two or if you have some finite bandwidth for the laser, you will find that every like several turns of this screw, your intensity was going down. This was happening because there was a very small bandwidth to the laser, and smaller the bandwidth, larger the distance after which this dimness comes in the pattern. If you have a sample which has a very broad wavelength, means a broad bandwidth, that is, it covers all the frequencies, then you will find that you will get almost everywhere, you will get disappearance of the fringes, as you observed in the experiment last time. And that is what you are observing here, that everywhere the intensity is close to zero. There is some oscillatory structure, but it is close to zero. And if you take a Fourier transform of this signal, what you obtain is this particular spectrum. Basically, this is a complicated time waveform. And what the Fourier transform does is it decomposes this into what are the sine waves which are present here, means which frequencies are present, which frequencies are absent, and then it plots. This is a function of wave number. Wave number is nothing but 1 over wavelength, which is nothing but frequency divided by C, basically. So this is basically a measure of the frequency only in some sense. And you can see that the spectrum shows you at which frequency how much absorption was taking place. That can be obtained from this interferogram. This is a very, very powerful and very, very neat technique, because normally there are several challenges in infrared spectroscopy. One is that the sources which you use for infrared are very dim, because if you try to heat them more than that, they turn into visible light sources because their black body temperature shifts. So they are by nature, they are very dim. Okay, and the detectors are also very poor efficiency. So you need to make up for all the time which you are keeping the instrument on by quickly getting as much of the spectrum as possible. And this is one of the ways which it is done, where all wavelengths are simultaneously incident, and you observe the interference pattern among the different wavelengths, and from that interference pattern you infer which all frequencies were originally present. That is how Fourier transform spectroscopy works. And this is just a schematic of how the actual instrument would be, that you have an interferometer here, so infrared source, then there is a beam splitter, and that beam splitter splits the beam into two parts. There are two mirrors, one is a fixed mirror and one is a moving mirror, and as the moving mirror moves, the interference pattern is generated in the detector, and then that interference pattern from the detector is taken to a computer, a Fourier transform is done, and you get the frequency spectrum in this kind of format. Means absorption or transmittance, whichever you prefer. Normally, the traditional way of depicting an infrared spectrum is as an absorption spectrum. So you have 100% transmission as the baseline, and anywhere there is absorption, you see a dip. So this is percentage transmission, which is plotted on the y-axis. This is the traditional way of depicting infrared spectra. This is a more complicated arrangement, but the same idea. There are two mirrors. One is a moving mirror and one is a stationary mirror. There is a beam splitter. There is an infrared source. And a laser is used as a reference just to know how much the mirror is moving. Because if the mirror is moving automatically, you have no control over, or you don't have to take reading of how much you are moving the mirror. Rather, that is automatically determined by using simultaneously a helium neon laser, which will tell you that where is the mirror by the number of shift in the fringes. So you get a very accurate map of distance moved by the mirror versus what is the interference pattern obtained from the IR. You get a very clear indication of that, and this is an inbuilt mechanism using a laser, so that the interferometer gets self-calibrated. The laser wavelength, once you know, you can determine how much the mirror is moving very accurately, and that can be used in turn to generate the Fourier transform spectrum. And this is what an actual spectrum looks like. This is a spectrum for a compound called aniline. It is basically a benzene type ring, except that at one of the carbons, the hydrogen is removed and a amino group, NH2 group, is attached over there. And for this particular substance, there are several important indications in the infrared spectrum. For example, this particular peak is because of carbon nitrogen bond, this bond stretching in the way in which we had described it earlier. Okay, so when you have this carbon nitrogen bond stretching, that particular one will be absent if you don't have the amino group. For example, if you take the spectrum for sada benzene, which doesn't have the NH2 group attached to it, then you will find that the carbon nitrogen bond stretching peak will be absent. So here you will just get a flat region and this peak will not be there. Similarly, here there is a NH bond stretching vibration. Again, this will be absent. This 1 to 3 peaks will be absent in benzene. In benzene, you will have only CH stretching and no NH stretching, because in benzene there is no N. Because it is aniline, you have this extra. So if I have benzene and aniline to compare, for example, I will not observe this peak, I will not observe this peak, I will not observe this peak also. This is again due to scissoring vibration of the NH2 or amino group. And you will not observe these also. These bands, 1, 2, 3, 4 of them, are observed only when there is a substitution on a benzene ring. Then this induces certain vibrations in the ring itself, and that is what leads to these bands. How do we come to know all this? Well, people did this manually for several decades. They figured out kya karenga to kab kya hota hai and so on. And then after they arrived at all these rules, they tested it against newer and newer compounds. And finally, it is very well established that whenever there is a single bond and it is stretching, then you will get vibrations in this region, more or less. That is from 2000 to 4000 centimeter inverse. The unit for wave number is centimeter inverse. You know that. Okay, then between 2000 to let us say 1200 or 1300, you have got other bending and other larger atom stretching vibrations, and double bonds and triple bonds will also show up in this region. And then in this region, between let us say 1200 and below, it is called the fingerprint region, because just by looking at this particular region, you can actually pinpoint. If you have a database of different compounds, you can actually pinpoint what is the compound. We are not going to do that, because then that defeats the whole purpose of what we are doing. So we will not be trying to do it automatically. There are infrared databases, and many times the instrument comes with a inbuilt database, so that on computer it records the spectrum, it compares, and it tells you yahi compound hona chahiye, and it gives you the confidence level, 95% confident or 97% confident that it is the same compound. That kind of automation is also available. But suppose you have a new compound which is not there in the database, then what will you do? That is what we are looking at. Okay. So this region between 600 to 1200 is called the fingerprint region, where you will actually find the fingerprint of the molecule. Different molecules will have different vibration, because these are complete vibrations of the entire molecule. So it will carry a chap of what the entire molecule is like. Not at all easy to understand why it is happening. I mean, you can do basic back of envelope calculation, but it is not possible to predict each and every peak very accurately using ab initio quantum mechanical calculation. It is not needed also, because already people have done all this homework. कौन से region में क्या आता है, and in fact you get ready-made tabulations like this, that कौन से type के compound में कौन से region में क्या मिलना चाहिए. So you get bending vibrations, stretching vibrations. If there is a triple bond, then it will come here. If there is an OH group, it will come here. If there is an aldehyde group, it will come here. If there is a carboxylic acid, it will come here. Then if there is an amine, then you will have some vibrations here, and then you will have some vibrations here. Then if there is an aromatic compound, you will have certain types of combinations at various places. So all of these tabulations are available. Okay. And probably I'll be giving you one such tabulation, so that will help you to analyze the spectrum which is given to you. This is the basic idea in infrared spectroscopy. My aim with this entire explanation was that to introduce you to the idea, and the further work required is that you have to go and read up on this particular thing, and try to understand it. And we'll have a further more pinpointed discussion when we meet next Wednesday onwards. After that, every Wednesday and Saturday we have lab. So each group, I think group number 8 is the first one to have this experiment. So group 8 and then group 7 and so on. So whenever we meet, we'll discuss it in further detail. Right now, few things which you can try to prepare right away. These are a few questions. I'll be sending this PPT. So anyway, the recording is also there. So no need for you to write down this right now. But basically, as part of your write-up, that is whatever you call fair journal or something for the practical, you need to at least find out answers to these questions. I leave the questions on the board if you want to write down, and if there are any doubts at this stage, I can address those. Please, कुछ भी doubt रहेगा तो पूछ लो अभी. You can probably unmute and ask, or you can type it in the chat, whatever. I'll wait for a few seconds. If no one raises their hand, then we'll go further. I know it is a very sudden and quite broad introduction, but if you have any doubts at this stage, you can ask. Otherwise, we can go further. Bolo.
Sir, in the last slide, You showed that the in double bond region we have more pronounced peak rather than in single bond region. Why it is so?
Let me come back to that slide. Yes, what was the question?
Aniline slide.
Okay, here na.
Yes,
See,
yes.
for aromatics, see, okay, for aromatic compounds, the vibrational bands are expected near 1600, 1500, and 1450 roughly. So we can see whether there are bonds. So this is 1500. This peak is there. This is the CC stretching, but it is the C double bond C which is here, na. It is that stretching vibration which is producing these bands. Okay. So in aromatic compound, you have C single bond C also and C double bond C also. Each of these corners has one carbon atom. I
Yes.
hope you know the benzene structure. So then this region 1500, 1450 and 1600. 1600 may be hota hoga, but it is dominated by the NH2 scissoring vibration. But here this is due to the CC stretching is C double bond C and C single bond C, the aromatic stretching. If you see the same one in alkane, sorry, wrong direction. If you see the same one in alkane, it is slightly shifted in the other side. It is near 1450 and so on. And if you see it in alkene, it is here. Aromatic bands are here because it is aromatic means it is partially, sometimes the double bond will be one side, partially it will be, sometimes it will be on the other side. So it occurs exactly between alkane and alkene. Between these two, the at that region you get the stretching vibration for aromatic compounds. So you are seeing those vibrations here for aniline. This CC stretching is not C single bond C, it is C with conjugated bond, that is single and double alternating bond like an aromatic compound. This is what you will see over here. Okay. Anyway, I think it is good, very nice question. And uh, I am sure many of you may not have fully understood. It is fine. The whole idea was to introduce that this search topic is there, and you can go and read in the references. You will get a better idea. Okay. These are a few of the questions which are there, which you need to know the answer. मतलब कम से कम ये experiment किया, मतलब इतना तो आना चाहिए. That is the kind of expectation. ठीक है. Basic physics and technical part. So if you can find out answers to this question and keep it, write it down somewhere, that would be very nice. Whenever you come for the practical, I'll ask you whether you have found answers to these questions or not. That will be part of the discussion. Okay. Moving further, the second segment for today is about nuclear magnetic resonance. Again, we'll go through a similar pattern, that how does it originate, what is the idea, what kind of instrumentation is used, and how it will be useful for us in the analysis. So my bottom line, coming back, my bottom line for the infrared, like I said, that different functional groups give you vibrations in different regions. So by looking at the spectrum and peak किधर है, you can actually pinpoint कि कौन सा functional group present होना चाहिए. ठीक है. Now coming to nuclear magnetic resonance, the idea in NMR is very simple. The idea is that अपना एक nucleus रहता है, उसको spin रहता है. Especially means consider proton for example, because in most compounds, especially organic compounds where IR is more dominantly used, IR is also used for semiconductor and other things, but dominantly used for organic compounds. Organic compound is a very wide branch, means you have paints, dyes, polymers, oils, so many different types of materials which need pharmaceuticals, which need this kind of analysis. Okay. NMR, nuclear magnetic resonance. The idea here is that you have a proton, and that proton has a spin, and that spin, when you place it in a magnetic field, it can either point in a spin up direction or a spin down direction. Spin down generally has higher energy than spin up because it is easier to orient in the direction of magnetic field and more difficult to orient opposite to the direction of the magnetic field. Okay. So the spin up and spin down two states are there, and in principle, once I fix out the value, the magnetic field value, these two will have some energy separation. And if I then give a signal which is having the same frequency, then it will induce the particle to go from this state to this state, and I will find absorption at that particular frequency. And I say that nuclear magnetic resonance has occurred, and I record at which frequency it happened, and I say this is the particular frequency at which nuclear spin resonance takes place. Nuclear magnetic spin resonance takes place. Here, a very important thing is that the splitting in the energy levels will be a function of the external field, because the energy of the spin up will be minus mu times b, mu being the magnetic moment, and the energy of the spin down will be plus mu times b. So the energy difference will be 2 times mu times b. Okay, mu is magnetic moment and b is magnetic field. This is fixed once you fix the field. फिर तुम बोलेगा इसमें मजा क्या है, फिर क्या होएगा? What happens is very interesting. So let us try to see that story actually. This is the experiment which was originally done in 1950s, and this was a Nobel Prize winning experiment for Purcell and others. Basically, what you do is something like this, very interesting. Actually, 1950s saw a lot of research which made use of megahertz, gigahertz kind of frequencies. Reason for that is during World War II, all the countries had a lot of radar equipment, because they had to do radar to find out किधर से submarine आ रहा है क्या, plane आ रहा है क्या, etc. So this radar equipment, once war was over, वो ऐसे ही पड़ा था. So then all the scientists said, अरे हमको दे दो करके एक करके all these 100 megahertz, 200 megahertz, 2.4 gigahertz, 10 gigahertz, all these kind of frequencies came in at that stage, because those of equipment pada tha. Very, very powerful RF generators were available, because you need radar to go to like several miles. So very powerful generators were available and they were lying unused. So all our scientists took it. So NMR आया उसमें से, particle accelerators like synchrotron were developed because there are RF technology was available. LINAC, linear accelerators were developed. So there was lot of development just because of the availability of this radar equipment at high frequencies. It's an interesting historical fact. I don't want to push that fact too long, because I'm not saying we should have war for scientific development. So don't take it in that sense. Just an interesting fact that why you saw a lot of new kind of fresh blood being pumped into science after 1950s is because there was a lot of leftover equipment from World War. Just a historical fact more than anything else. Basically, there are two magnetic pole pieces of iron and there is a coil around it, and a magnetic field is generated in this direction, which he has called as Z direction. There is a magnetic field B0 in the Z direction, which is called a steady field. And then there is a oscillatory field. There is a coil with a AC current flowing through it, and the coil is like this, and so the magnetic field will come out of the plane of the paper as it is shown over here, this arrow along the x-axis. This is the magnetic field B1, which is an oscillatory field. And basically what you do is, because of the steady field, all the nuclei in this substance, the gray colored object here, are going to align either spin up or spin down. And then you perturb it using this oscillatory field. And as you change the frequency of this oscillatory field, what will happen? At one stage, suddenly a lot of absorption will take place. And as soon as the nucleus absorb, it will re-emit. And that re-emitted radiation comes out isotropically, and you have a detector which detects that. And as you move the frequency of this oscillator from one side to the other, you find that this was ethyl alcohol which they used, and they found 3 peaks, 1, 2, 3. And then they said maybe this peak is bigger, so it is because of CH3. This is smaller, it is because of CH2. This is even smaller, it is because of OH. I mean, they didn't say just like that. They had some reason for that, but we'll come to that reason in a while. Okay. But this is the basic idea. Have a steady field, have an oscillatory field, and have a detector. That's the basic idea of NMR spectroscopy. I am not going to go into further details, but the basic idea is that if there is a current loop, it can detect a magnetic field, and if there is a If there is a current loop, it can generate a magnetic field, and if there is a loop without current which is placed in a magnetic field, then current will be induced in that. These are the only facts which are used in this entire experiment. You can read the reference for further detailed explanation of this particular figure. Okay, this is the basic idea and how it works. Why do you get three different peaks for three different types of functional groups? This is CH3, this is CH2, this is OH. You get three different peaks. What do you mean by three different peaks? They are the hydrogen in OH, the hydrogens in CH2, and the hydrogens in CH3 are experiencing this resonance at three different frequencies. According to our original logic, that is not possible. जब मेरा magnetic field fix है तो सबका resonance एक ही frequency पे होना चाहिए. ऐसा क्यों नहीं होता है? Because in the vicinity of OH, the electron structure is different. In the vicinity of CH2, the electron structure is different. In the vicinity of CH3, electron structure is different. And electron structure different रहने से क्या होता है? Applied magnetic field is in the up direction in this diagram, and that causes all the electrons which are already there, and electrons are moving in their orbits. It causes them to cause a secondary current, and that secondary current can either assist or oppose this magnetic field by an amount which is given by sigma times B0, where sigma is some proportionality constant. External field जितना ज़्यादा रहेगा उतना ये असर ज़्यादा मिलेगा, and this effect can either reduce or increase the existing field, and so you will get a shift of the nuclear magnetic resonance depending on what are the electron structure surrounding that particular nucleus. It is summarized over here. The nuclear spin interacts with external field B0, but the electrons in the molecule also react to B0 and they generate currents. When they generate current, due to that current, there will be a secondary magnetic field which you can write as sigma times B0. So the effective magnetic field B is actually B0 plus or minus sigma B, depending on what direction the secondary electrons are going to create the secondary currents. And the effective magnetic field thus depends on the environment. What are the surroundings? Surrounding में ज़्यादा electron है, कम electron है, ज़्यादा energy वाला electron है, कम energy वाला electron है. All these things come into the picture. So basically, in OH, there are two lone pair of electrons with this oxygen. So the hydrogen which is attached to the oxygen experiences a different electron surrounding. The one which is at the other end in the CH3 group experiences a different type of surrounding, and the middle one gets partially this and partially this, all the influence, and so you get three different peaks, even though the hydrogen atom which is present in all the three is the same. You get three different peaks because the surroundings are different. This is a very, very interesting and actually very, very amazing thing, that the nucleus which is present, you don't expect it to kind of get affected by anything, but it is affected by the surrounding environment, and therefore nuclear magnetic resonance spectroscopy can tell you how many different types of proton are there in that organic molecule, what are the different situations in which they are facing. To give you an example, again I am taking the same compound, aniline. Aniline is basically CH, 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 CH with a alternative double and single bond structure, and C, and instead of H here you have NH2, like we have discussed already. Now, if you notice closely, there are two hydrogens attached to the nitrogen, and there are 1, 2, 3, 4, 5 hydrogens attached to carbon. This peak corresponds to the hydrogen which is attached to nitrogen. Then these two hydrogens, 1 and 2, which are labeled as C, you can see that both of them will basically experience the partially the field of this nitrogen also, because this fellow has a lone pair of electrons which will be hanging around somewhere, and so this C peak is shown over here, and these A and B type of peaks are coming up over here. So you have got three different categories of peaks because you have got hydrogen atoms or protons in three different physical situations. Actually, these A and B are also slightly different. So you can see some splitting of one of these peaks into further peaks. A better NMR spectrum will give a cleaner result. This is just an example. Okay. But the idea is that if I know that different peaks are supposed to come at certain points, then I can pinpoint what is the type of functional group arrangement and what is the type of surrounding which the proton is facing in different compounds. For example, and basically the scale which is there on the bottom is something called the chemical shift scale, which is basically the absorption frequency for the sample minus some reference absorption frequency, the difference between these two, and it is expressed in parts per million. That is why you are multiplying by 10 power 6 over here. And this chemical shift is measured with respect to a standard sample, which you have to find out. That is homework. What is the standard sample which is used for NMR? Okay. But basically the idea in NMR is that it will tell you if different protons are there in different types of surroundings. And there are ready-made tables of that also available. That chemical shift means when you have a halogen, then chemical shift will be between 6 and 2. Whenever you have a aromatic with a phenolic kind of component, the thing will be between 5 and 10. If it is aromatic with only hydrogen, then it is narrower. So this is what you observed for the what you say, these bands. These two bands are from this category, aromatic. And amino group is not mentioned over here, but you can see that there is a CH with an N. And so that is basically coming here somewhere between 3 and 4. So that is, sorry, that is this one somewhere here. So you know that there is a nitrogen, then you will get a peak somewhere between 3 and 4. And if there is aromatic, you will get it somewhere between 7 and 8. And that is exactly what you are observing over here for aniline. So the NMR plus the IR can usually help to clarify completely what type of compound you are dealing with. And if you combine this with the total mass of that particular compound, then you can also zero in on what is its actual structure. Because once the mass is known, you know limitation on number of atoms, etc., which you have. Okay. Again, there is some kind of homework type thing for this particular part, that is part of the write-up. You have to cook up the answers to this particular thing. I will pause at this stage. If you want, you can write down these questions. And if anyone has any doubt about the NMR part, you can please ask, or about the IR. Either way, we are doing well as far as time is concerned. So you can actually do that.
हेलो
Yes, बोलो.
सर, वो लास्ट का जीरोइंग ग्राफ का वो वाला,
कौन सा ग्राफ?
वो टोटल मास अपने जीरो जो ग्राफ NH4 वाला,
कौन सा वाला यार?
सेकंड लास्ट,
ये वाला?
और एक स्लाइड आगे.
हाँ.
और एक, हाँ, यहाँ पे जो आपने बोला ना जीरोइंग वाला पार्ट, NH3 और CH4 अगर टोटल मास मालूम रहेगा तो हम लोग जीरो कर सकते हैं. वो वाला पार्ट एक बार.
No, what I meant by zero in means you can pinpoint what is the structure. It is just a muhavra. Zero in means you can pinpoint what is the structure, because see, अभी तुमको functional group मालूम है. You know that it is aromatic compound. You know it contains nitrogen, but you still don't know whether it is benzene based or naphthalene based or anthracene based. Means aromatic compound can be of different sizes. Now one single ring means benzene, two rings joined together means naphthalene. Then there is anthracene, and several types of aromatic compounds are there. So at one stage, the functional group analysis from IR and NMR will only give you what type of compound it is, but it will not be able to pinpoint many times what is the exact size of the compound. because it will show, see if the compound, for example, let me take a simpler example. Suppose I give you methane, ethane, propane, butane, pentane, hexane. These are all normal compounds, chain compounds of carbon. Okay, all of them will have the same characteristic. All of them will show only the normal this kind of means chemical shift. It is just a CH this kind of thing, and you will not get to know really whether ये इसका length कितना है, whether it is 5 carbon atom, 6 carbon atom, 7 carbon atom, 8 carbon atom. If you have a mass spectrum, then you know, because 8 carbon atom means each carbon atom mass 12. So 8 carbon atom means mass will be around 96, that is around 100 or so, somewhere there. On the other hand, if there are only 3 carbon atoms, then the mass will be close to 36 or something like that. Okay, so you can pinpoint the structure if you have the mass spectrum also. If you don't have the mass spectrum, you can only talk about ये ऐसा टाइप वाला कंपाउंड है, it is a alcohol or it is a phenol type or it is a alkane or it is an alkene or it is a ketone, whatever. But you cannot pinpoint the structure. To pinpoint the structure, it is important to have the mass spectrum also. That was my point. Is it okay?
Yes sir, yes.
Yeah. Anyone else?
Sir,
हाँ जी.
on the x-axis we have parts per million. So
That's right.
Does it mean that it also gives the relative abundance of the bonds?
It is not relative. No, it is parts per million of chemical shift. So means basically you will obtain resonance for your standard sample at some particular frequency. Okay, and you obtain resonance for your actual sample at some other frequency. For example, 4.0005 megahertz suppose is the resonant frequency for your standard, and for a sample it is 4.0006 suppose. Okay, so that difference of 0.0001, that divided by the original frequency, this particular quantity is called chemical shift. Okay, and that chemical shift is experienced in parts per million, in the sense it is multiplied by 10 power 6. So it is basically, when you say that, let me take this as an example. When you say that I have a chemical shift of 5, okay, parts per million, what I mean is that the difference in the frequency between my sample and the standard sample divided by the applied frequency, this ratio is 5 divided by 10 power 6. So it is 5 parts per million, which means that it is actually, means this parts per million actually means bracket into 10 power minus 6. That is what it actually means. It is just a terminology which is used, parts per million, but it is not talking about concentration. It is talking about ratio of frequency difference divided by actual frequency. That is what it is talking about. Okay, it is not at all related to the concentration.
Okay, sir.
Yeah. These are some questions which are there, that what is a typical energy scale. This is just more for like exercise for you to understand the scales involved. And this is important. What is a standard or reference sample used to define chemical shift scale, and why that particular one is used? Why not some other one? And then list any 3 applications of NMR other than this one. Explain one of them in detail. This is just homework for you, so that तुम लोग जाके पढ़ोगे. These are the minimum things we should know once you have done this experiment. Again, I am saying, means if someone tells me from some other university, some student tells me, sir, मैंने IR or NMR किया है MSc में, then my expectation will be that they should know at least this much, if not other things. So this plus whatever we have given for the IR also, please try to prepare all of that. Okay, I am moving further from here now. हाँ, yes.
सर, अगर हमारे कंपाउंड अगर रेजोनेंस शो करते हैं, तो फिर वो स्पेक्ट्रोस्कोपी में हमें कैसे मालूम पड़ेगा? लाइक एक अगर डबल बॉन्ड वापस बोलो,
मेरे को सुनाई नहीं दिया.
हाँ सर, अगर हमारे लाइक बेंजीन कंपाउंड अगर रेजोनेंस शो करते हैं, लाइक सिंगल बॉन्ड डबल बॉन्ड में जाता है और लाइक ट्रांसफर ऑफ इलेक्ट्रॉन से, तो वो हमें स्पेक्ट्रोस्कोपी में कैसे दिखेगा?
You are talking about the conjugated bond structure, right?
Yes, sir.
So that toy picture which chemists like to make, where one electron transfers to the other place, all that is just not the correct picture. The correct quantum mechanical picture, you can actually, for benzene, it is a nicely symmetric molecule. With group theory, you can actually derive what are the lower orbitals, lower molecular orbitals. So some of them are delocalized orbitals, where the electron is free to roam among all the 6 carbon atoms. Some are partially localized over 3 and 3 carbon atoms also. So all that picture of electron jumping from here to there and इथे असता bond किंवा तिथे असता, all that is toy picture, which because chemists like to visualize things, they do that. But as a physicist, that kind of picture is not quantum mechanically accurate. Quantum mechanically, you are in a superposition state actually. Superposition state means what? Superposition state means you have 50% probability of electron being here and 50% there, and unless you go and measure the electron, you don't know where it is, right? And you are not going to go and measure the electron because you are not probing the actual whether it is a double bond or a single bond. You are not probing that. The result which you are expecting is that there is a particular electron density distribution, which can be means basically electron wave function whole square will give you electron density distribution, and with that density distribution, when it interacts with the magnetic field, it causes a certain amount of shielding. So from the practical or experimental viewpoint, you have no clean way of probing whether, means you don't actually probe, or you don't actually collapse the wave function of the electron on one or the other bond. Basically, you let it remain as a superposed object and you don't measure the electron at all. So that question of this thing, the dancing of the electron, which is there in chemistry books, it is not a fair description, and in particular here you are not probing that aspect at all. That is part of the answer. And the other part is that in the spectroscopy, in IR spectroscopy, the bond strength and therefore the bond vibration frequency, it is taken as an average one for all the bonds being equal. So for benzene, you will get one band and not two different bands, one at double bond frequency and one at single bond frequency. You will get combined bands at the in between frequency, because the bond strength is like 1.5 bonds kind of roughly. And in NMR spectroscopy, uh, again the electron density distribution is taken, and therefore between two different sites which are supposed to have alternate single and double bond, no distinction is made. Okay. So spectroscopically, you are not probing at all this kind of thing. That is how I would answer that question. Okay. Is it okay?
Okay, sir. Yes,
And
thank you, sir.
and thank you for raising the point that the reference book which I have given, many of them are chemistry oriented reference books, because उसमें बहुत अच्छे से दिया है कि ये करना कैसा है. But don't take too seriously the explanations which are given in those books, because they are more visualization and chemistry oriented. But from a proper physics viewpoint, those explanations may not be necessarily very accurate. Okay. So we'll discuss that when we come to the details, when we come to the actual practical. Allow me to move on to the next topic, which is mass spectra. Here I am just going to give a very basic idea and close. It is not like no details, etc. Basically, how a mass spectrometer works is you inlet a particular substance, usually in gas phase, and you inlet it into an ion source which will ionize that particular ion source. Means this is the sample which is ionized in that region, and that ions are then passed through a mass analyzer. Mass analyzer is usually a configuration of either electric field using two plates, parallel plates, or a magnetic field, or a combination of the two. The idea being that the different masses with the same charge will bend by different amounts once it is placed in the magnetic electric field or magnetic field. You know this because you know that the electric force and magnetic force are dependent on the value of the field. but force is mass into acceleration, so you will get the bifurcation of them. If all of them are having the same charge, you will get the bifurcation according to the mass. That is how the basic mass spectroscopy works. And after the mass is analyzed, that after passing through the mass analyzer, all the different components are moving in different, slightly different directions. All of them will be incident on some kind of transducer. It could be a photographic film, it could be something more sophisticated. And bottom line is that you get a spectrum which looks like this. This is a spectrum of methyl alcohol. And methyl alcohol, you can calculate the total mass. Carbon is 12, oxygen is 16, that is 28, plus 4 hydrogen, so 32. So you can say that at 32 you will get some fraction you get at 31, 30 very small fraction, then 29, 28 very small fraction, and then directly you have got 16, 15, 14 and so on. So basically this is the entire molecule. This is molecule after losing one hydrogen atom. See, in the process of ionization के साथ साथ, ionization means basically molecule को लेने का, उसको मारने का जोर जोर से, एक इलेक्ट्रॉन निकलने के मोटिव से. पर तो इलेक्ट्रॉन निकलने के चक्कर में कभी कभी बॉन्ड भी टूट जाता है. So mass spectrum always looks like this. So you have to look for the highest mass fragment and say that this is the actual molecule, and all the other fragments will tell you molecule के क्या क्या टुकड़े हो सकते हैं. So 31 mass fragment means basically CH3O, one H is removed. Then 29 mass fragment means 2 hydrogens are lost from somewhere, or sorry, 3 hydrogens are lost from somewhere. Then mass 16 means just the oxygen. It could also mean a C and 4 hydrogen, unlikely, but it is there. And mass 15 means C and 3 hydrogen, mass 14 means C and 2 hydrogen, and so on. So you can actually analyze this in detail, and this is subject of its own right, that depending on what are the conditions in the ion source, you will get different fragmentation patterns, etc. That is why I am not going into the details. The aim of mass spectroscopy, as far as our this particular activity is concerned, the mass spectrum is only for confirming to you what is the molecular mass, so that you can fix out the molecular structure. For example, if I find that in IR the alcohol bands are present, and in NMR I find that alkane type of bands are present, then I know that this is a normal alcohol, but I still don't know whether it is methyl alcohol, ethyl alcohol, propanol, isopropanol, etc. Okay, how to find that out? मास स्पेक्ट्रम पे जाने का. मास स्पेक्ट्रम में मालूम पड़ेगा कि टोटल मास कितना है, उसमें से अंदाजा लगा, उसमें से अल्कोहल है ये IR से मालूम है. सो यू से दैट O is 16, H is 17, उतना माइनस करने का. जो बचा कुचा है उसमें कुछ कॉम्बिनेशन बैठता है क्या, कार्बन एंड हाइड्रोजन क्या, ऐसा देखने का. ऐसा करके करके यू विल फाइनली गेट द स्ट्रक्चर. ठीक है. सो फॉर एग्जांपल प्रोपेनॉल एंड आइसोप्रोपेनॉल, द IR will be similar but NMR will be different. We'll be doing this in the practical class, so don't worry. I'm just telling you for information, and those of you who could try to figure it out at home, I'll be very happy. Propanol and isopropanol, or propyl alcohol and isopropyl alcohol, or 1 propanol and 2 propanol in the IUPAC nomenclature. These have basically same molecular weight. They have similar IR spectra, but the NMR will be different. On the other hand, if you have propanol and butanol, then IR will be similar, NMR will also be similar, but the mass spectrum will be different. So depending on pairs of compounds, you can easily identify which is which by using all three together, IR, NMR and mass spectrum. So that is the basic idea for this particular experiment. Now let us quickly go to what exactly is expected from your side. So तुमको करना क्या है experiment? So this is the procedure which I am intending to follow. That we will split up. Already we are in groups of either 6 or 7 students. What I saw, 7 है actually, but उसमें से कुछ लोग गायब है, वो भी मालूम है मेरे को. So we will break up into, depending on the number of students. If there are 7 students, then 2 plus 2 plus 3, 6 जन है तो 2 + 2 + 2, 5 जन है तो 2 + 3, 2 ही ग्रुप बनाएंगे, 4 ही जन है ग्रुप में तो 2 का 2 ग्रुप बनाएंगे. विल स्प्लिट इनटू सब ग्रुप्स. बॉटम लाइन. ठीक है. Each subgroup will be given one particular spectrum, IR, one NMR, and one mass spectrum of the same compound. And then you have to sit and break your head, discuss with each other, and come out with what do you think is that particular compound. Okay. Using whatever the information I have given today, plus lot of reading work involved from your end, you can sit down with a book of means one of the reference book which are there. Any one of them is sufficient for doing this analysis, but I have given 3 reference books. Okay. You have to go through this. Okay. IR, NMR, and mass spectrum, and not identify means you have to actually go through it, see correlation क्या है, हा स्पेक्ट्रम ह्या कंपाउंड मी म्हणतो तर का तसं, why do you feel that, why do you think that this spectrum is of this compound only, some kind of reasoning out should be there. Okay. And then means in the morning of each Wednesday or Saturday for the respective group I will give the compounds, and then we can regroup in the afternoon. Afternoon means whatever 4 o'clock or something, where we will have a discussion about what all you have managed to do and whether you managed to identify or not. नहीं हुआ तो क्या गड़बड़ है, किधर अटक गया, all those things we'll do that. ठीक है. So that at the end of the day, whatever compound given to you, IR, NMR, and mass spectroscopy, you should be able to pinpoint most of the things in each of the spectrum की ये spectrum में ये feature क्या है, इधर ये क्या है, इधर ये क्या, all those things. ठीक है. That is the learning aim of this particular experiment. And after we finish this discussion, then in between anytime you can catch me if you want further discussions. But the idea is that roughly 2 weeks after your experiment is over, you have to submit the write-up. Write-up में क्या क्या चाहिए वो भी बता देते हैं एक बार. So-called fair journal. Every student has to submit. 2 जन ने ग्रुप में किया तो दोनों ने लिखो. सेम लिखेगा चलेगा, मेरे को चलेगा, but you have to write. ठीक है. एंड हाउ टू राइट एंड व्हाट टू राइट मैं प्रदीप सर से पूछ के तुमको कंफर्म कर रहा था, वेदर सॉफ्ट कॉपी ही देना है कि एक्चुअल जर्नल बनाना है बाइंडिंग वाला वगैरह अपन देखते हैं. ठीक है. मोस्टली वी विल गो फॉर जस्ट सॉफ्ट कॉपी और इवन हैंड रिटन इन योर होम एंड देन स्कैन कॉपी इफ यू डोंट हैव प्रॉपर फैसिलिटी टू टाइप और समथिंग. ठीक है. बट यू विल हैव टू डू दैट. So your write-up will consist of the following things. One is whatever questions were there in segment 1 and 2, IR and NMR के बारे में, उसका सबका explanation, half one paragraph roughly. If you want to write more, most welcome, but at least one paragraph to describe the answers to those questions. And then detailed report of your identification of the compound, which is given to your subgroup. That compound, each subgroup will get different, all 3 will be related to each other. So in the afternoon when we discuss, we can contrast and compare and try to figure out that how the differences are arising and so on. Means for example, one group will be given benzene, second subgroup will give aniline, so you can compare how the 2 are differing from each other. And we will also means that is what we'll have. You should also note down briefly the point of comparison with the other subgroups. Okay. And if we have in the discussion, each time I will give 1 or 2 questions to each subgroup, 1 question at least, उसका भी आंसर तुमको बताना है. ठीक है. That will be mostly related to your analysis and how you present and so on. There are marks for all these activities. If you don't do or you fail to do some of these things, at least my internal marks will go to Pradeep sir, and that will have those particular just means if you have not done well kind of remarks will go. So please be careful and do it sincerely. ठीक है. Any doubts on this part? Hello. हाँ ओके गॉट इट. नो सर वाले नहीं चाहिए, जिसको डाउट है वो लोग ने पूछने का. नो सर ओके, दैट इज लाइक डिफॉल्ट आंसर, आई नो. ठीक है. देन वील मीट ऑन व्हेनेवर द नेक्स्ट सेशन मींस आई थिंक 2 हफ्ता तुम्हारा ये है ना, 2 weeks you have what you say instructions. I think 21st or something is the first date for the practicals. So group number 8 I think is first. So this is experiment number 8. So group number 8 has that experiment during 21st. We'll meet at that time. ठीक है, उसमें सब ये सब रेडी करके आओ. Whatever the questions are asked ना in segment 1, segment 2. Anyway, I'll share this video also and we'll do that. ठीक है. Anything else? Again, since I have 4 minutes left, let me just re-emphasize one thing, that what is the broader physics aim of this. See, I am not intending that each and every one of you will go into organic analysis and become some kind of either pharma or polymer kind of person. No, the idea here is that how to work with multiple correlated data sets. That is the concept behind this experiment. That if you are given multiple data, for example, if you are working in material science, normally to characterize a material, you need either TEM, Raman, FTIR. Means there will be 3 or 4 correlated measurements which you make, and you make means main conclusion from one measurement and confirmatory conclusion from the other measurement, and vice versa. Like that, you can draw several conclusions about the whole material. If you are working in nuclear physics, you can or particle physics, you will have supplementary data from some other detector, and your main detector may be a gamma ray detector. There will be a supplementary detector, so for example, a particle detector. So that can help you to measure the interaction cross section. So because the interacting beam will pass through your sample and get Rutherford scattered at a certain angle. So you can measure the absolute cross section, simultaneously get the radiative process which you are interested in. So each and every field, there is always the possibility that when you do a realistic experiment, there will be multiple measurements going on simultaneously, and you should be able to correlate and combine the effect of these multiple measurements in order to fix out the final physical outcome of that particular experiment. For example, if I do a scattering experiment and I measure the data coming from the target sample, but I don't measure the original beam current, or I don't control the original beam energy, then that data becomes useless as far as drawing any scientific conclusion is concerned. So you need multiple data sets many times to arrive at a logical and correct conclusion. And of course, if you do 3 experiments in the lab, one in NMR, one in IR, and one with mass spectroscopy, you will not get the feel which you will get when you do this particular activity. So this gives you something beyond what you would have got when you would have done the experiment hands-on. This was the aim, or this was the theme for this particular semester, that we should involve experiments. So-called experiment means practicals, in which तुमको अपना दिमाग यूज करके you have to analyze a particular data set and develop the skill of doing that. ठीक है? So I think that this particular practical or experiment, it meets that aim. Okay, and we will discuss this in detail whenever we have the regular practicals. Thank you very much. I think my time is just getting over, so we can stop here. Any questions? Last chance for asking questions.
Sir, you said
बोलिए.
You said that there is a difference between IR and NMR spectra of 1-butanol and 2-butanol.
Yes, there will
so
be.
IR will be same just because there is a same shifting due to OH group, right?
Yes.
And NMR will be different just because of different coupling of H, because surrounding of OH group.
Surrounding of the H is different in. I was talking about propanol and isopropanol. Isobutanol will be slightly more complicated, but I was talking about propanol and isopropanol.
Okay.
But the surrounding of the H is different. So in isopropanol you will get only 2 peaks. In propanol you will get 3 peaks, and one of those peaks will be further split. So you will get basically 4 peaks. In propanol, in isopropanol you'll get only 2 peaks. In NMR means 2 major peak clusters basically. Okay.
Okay.
Good, but very very good question and very correct understanding from your side. Very good. अच्छा लगा, मतलब एक जन को तो समझ में आया क्या बोल रहा था मैं इतने देर से. So that is good. ठीक है. So I think you have your next session now. So we'll conclude this over here. Thank you very much.
Thank you, sir.
चलो. पढ़ा